Hi, thanks for joining us today. Today we're going to be talking about inverse trig and up to and including their derivatives. I think the derivatives will fit into a separate video, so we're going to get into that a bit later. It's a little bit sad because after those derivative rules, you're done. You're done with derivative rules. So sad for me, proud for you. Happy, happy, happy times are all ahead. Here we go. So the first thing I noticed about that paragraph is that is not correct. Should probably be are. I think none is treated as plural. I was debating with myself a moment ago. Whatever. So what we want to make sure we do is that since none of them are one-to-one, none of them have an inverse function. You should remember that to have an inverse function, you have to pass the horizontal line test. That means you have to be one-to-one. It also means you have to be monotonic. This is all covered in 7.3. You might want to go review that if you have a chance. 7.3 tends to be one of the weirder spots in that calculus, whatever. None of the 6 basic trig functions are one-to-one, so none of them have an inverse function. However, if we restrict the domain, the trig functions will become one-to-one, so they have inverses. So none of them are one-to-one, right? Here's what one-to-one means, passing the horizontal line test. Why don't they pass the horizontal line test? Because they're wavy people. That guy's not going to pass the horizontal line test. Look how many times he passes through the same y value. That one's signed, by the way. So we're going to restrict the domain of the trig function, which will in turn restrict both the domain and the range. So the way we've chosen to do this as a species is for sine and tan, we restrict the range to pi over 2, to negative pi over 2 to positive pi over 2, inclusive for sine, exclusive for tan. Exclusive for tan because pi over 2 and negative pi over 2 are asymptotes for tan. So we're not including these. We're not including these endpoints because tan has asymptotes here. For cosine, we have to use a different value. So sine and tan will all hit be one monotonic from negative pi over 2 to positive pi over 2. We're basically chopping it off here and here. It's monotonic on that range. Cosine, on the other hand, on that range looks all non-monotonic. He goes like this. So for cosine, we're going to cut him off from here to here. And that's why he has to go from 0 to pi. You don't have to memorize why they have the domain. You have to memorize those domains. And one final note, not cosecant. You would also call this y equals sine inverse, but it's not cosecant. Arcsine you need to know. If you're like, well, I'll just always write that, that's fine. You might confuse it to cosecant because cosecant is 1 over sine, in case you're still having trouble with that. But arcsine is going to show up on the test over and over again. We prefer arcsine, we prefer arccosine, we prefer arctan as calculus students because they're not ambiguous like this notation. So what are we going to do? Arctan is the only one with a nice domain. Arctan is going to be pretty intense. All right, let's get some graphs. So it's the inverse function. So I'm kind of thinking, we're thinking that if y was arcsine of x, sine y equals x. That's what it said in the table. So we're thinking about who the old pairs were. Well, when y was pi over 2, sine of pi over 2 is 1. Did you get it? Time to memorize. Sine of 0 is 0. Sine of negative pi over 2 is negative 1. Now, don't just connect them on a straight line. That'd be really stupid. What they look like is sine. If you swilted. If you switched sign around, that's what this should look like. So something like this. Oh my gosh. I jinxed myself again, but I'm so proud of that first part. That's what we're talking about. Not with that weirdness at the end there. Just pretend I did it perfect. I'm not going to edit it. All you people are like, just edit your video. No, I'm not going to. I won't give in. So there we go. It kind of looks like sine. It got restricted. You need to put those dots. If you don't put those dots, you're not getting the problem right. And we just got those values from looking at the y coordinates. Same thing with this one. You should be able to do this one on your own. 3, 2, 1. So we're thinking about cosine of 0. Cosine of 0 was 1. Cosine of pi over 2. Cosine of pi over 2 was 0. Cosine of pi. Cosine of pi was -1. Did you get all those? If you're confused why I'm plugging in y, it's this. We're thinking cosine y, cosy, equals x. And again, we want to have a nice sine looking guy. Well, don't tell cosine, but he looks exactly like sine. You know, I kind of stole that out, but who wore it best? Lame jokes. All right, tan, arctan. Arctan, top tier function. Arctan is probably the most beautiful function. Can you hear that playing? I can't believe this. The most beautiful, I'm not recording it again. The most beautiful function. Just listen to the dulcet tones of my voice. The most beautiful function of all is arctan. And here's why. Well, if we're thinking tan y, this has nothing to do with it, tanny. If you're thinking tan y is x, well, it goes through the origin. We really like functions that go through the origin. That's pretty important. What about 1? Who's going to get us 1 out of tan? Tan of blah equals 1. What if we try to solve that equation? What do we plug into tan to get 1? It's going to be pi over 4, so it should happen about halfway. So you should know that that's pi over 4. That would be helpful information. And likewise, we'll hit -1 at negative pi over 4. Womp. And here we go. What happens at these two angles? Well, tan of pi over 2 is undefined, but what's the graph of tan look like? Tan has a vertical asymptote at pi over 2, so arctan will have a horizontal asymptote. Wow, choked on that word because I said it with horizontal, not horizontal. And tan of negative pi over 2 will be a similar horizontal asymptote, but on the left. So what we're talking about is a function that is always increasing, has a nice behavior on the ends. I can't get it to just go straight up. Okay. I wonder if I'll edit these out. Probably not. Now, Francis Doctolero really objected to saying it was beautiful. I'm not happy enough with that. Okay. And it is beautiful. Like, it's not a debate. It's too much to straighten on. There we go. It just is beautiful. Looks kind of goofy right there, huh? I think it's because it is like this. There we go. It just is a beautiful function. And we're going to find out more about why it's beautiful in a second. So it's always increasing. It has very nice features, some inflections. It's the only inverse trig function that has a domain of all real numbers. Domain's all real numbers. It has a really small range. It's just a great function. Enough said. Right, Valeria? All right. Here's a helpful range chart. Range chart. Whatever. A geometric representation of the range values is shown right here. So arcsine is only covering quadrants 1 and 4. It's important to know arcsine is going to be using negative theta values. Arcsine is going to be spitting out negative theta values. Arcsine only can spit out values there. Can only give you angles there. Our cosine is quadrants 1 and 2. So that makes our cosine kind of nice, but it's also kind of annoying because it's different than the other two. And then we have the weirdo, the man, the myth, the legend, arctan, which covers quadrants 1 and 4 also, but it doesn't ever hit pi over 2 and negative pi over 2 because, again, arctan is not defined there. Sorry, because tan's not defined there. And we have our horizontal asymptotes on the graph. The two biggest mistakes that students make with inverse trig functions are putting inappropriate range values for an answer, which this chart should help you stop, and putting more than one range value as an answer. So for example, arcsine of negative 1/2 is negative pi over 6. It just is. Whereas some students will write arcsine of negative 1 over 2, 1/2, negative 1/2 is 7 pi over 6 or even 11 pi over 6. So what are they thinking? They're thinking, oh, well, gee, if I have 1 over 2, if my y is negative 1 and my height is 2, my hypotenuse, there we go, not height. If it's negative 1 and 2, I can have this triangle or I can have this triangle. Now this triangle could be hit with that angle, which is 7 pi over 6. And the other triangle could be hit with 11 pi over 6. So why are we only limiting it to negative pi over 6? And that's the next question. That's the example. Why are these wrong, even though it's true? It would be true that sine of 7 pi over 6, I mean, look at it, is negative 1/2. And sine of 11 pi over 6 is also negative 1/2. So why do we only pick one value? That's too much of a hint, maybe? Pause it, write something down. Just write something down. 3, 2, 1. We need only one value in order, training's bad, in order for the inverse function to exist. That's it. If we had all these other options, we'd have all these other problems. We wouldn't pass the horizontal line test. So even though all of these will output negative 1/2, you cannot say 11 pi over 6 is arcsine of negative 1/2. It's not as simple as thinking about which angle gives you that. And again, negative pi over 6 is this triangle. We're talking about this triangle. So it's really confusing to some students why it can't be 11 pi over 6. It can't be 11 pi over 6 because if we want to use these values of theta, we want all of these values. We definitely want the first quadrant. We'd have to go all the way to quadrant 3 to get the other values we want. The only way to get the values here is to go also down toward the negative angles. So it's because we want to be monotonic and we want quadrant 1 angles. If you can't read my ugly handwriting, that's supposed to say quadrant 1 angles. We want the quadrant 1 angles, and we need everything to be monotonic. We can't go like this, not monotonic. We have to go backwards, and backwards means negative angles. Feel free to watch that part of the video again. I thought I'd disable this for longer than an hour. Whatever. Sorry for the color. Don't care. Here we go. So evaluate this without a calculator. Evaluate all these without a calculator. You should be able to do this. You should have seen this last year. Try it out. If you have trouble, unpause the video, see how I do it, and then try the next one. 3, 2, 1. So we're thinking of arctan 1. You might know this by heart. That would be ideal. But we're trying to say tan of what equals 1? Well, there's 2 angles that would go in here. There's pi over 4 and pi over 5 pi over 4. But we can't use 5 pi over 4 because 5 pi over 4 is not in the range. So we're only talking about pi over 4. What do I mean it's not in the range? Look at our options. We only have quadrant 1 or quadrant 4 to work with, so we have to pick pi over 4. Our cosine negative 1. Our cosine tends to be a little easier. So we're talking about quadrant 1 or quadrant 2. Cosine, this is what I'm thinking mentally. You don't necessarily have to write this down. You can. Cosine of what will be negative 1? Well, it's almost certainly pi. Can you do the other two? Can you? So sine of who is going to give me negative root 3 over 2. Sine of who gives me negative root 3 over 2. So root 3 over 2 you should recognize as important. It's definitely pi over 3. It's a pi over 3 type angle, except we need it to be the right kind of angle. So it's not, okay, hopefully you didn't put 4 pi over 3 or 5 pi over 3. They're both wrong. The correct answer is negative pi over 3. Because that's in quadrant 4 with the right rotation. Last but not least, arcsine of 2. So which angle gives us 2? Sine of box gives us 2. This is impossible. Because sine is always less than or equal to 1. So we can't get arcsine bigger than 2. Again, you go back to the range. That's another way to do it. The domain of arcsine has to be a value between negative 1 and 1. Because the range of sine is only between 1 and 1. Negative 1 and 1. Okay, let's go on. Use a calculator to evaluate. My calculator is not reset. You're going to see stupidity from the last lesson. How do we use arcsine? There's no arcsine button. Again, your calculator doesn't know the better name. So you're going to use sine inverse. And why didn't they give it the better name? Because sine inverse fits a lot better on the button than arcsine. So second, sine inverse. I swear to God, you better be in radians mode. 0.3, enter, and there you go. There's your angle. That's not simplified, by the way, so that's not simplified. So we had better say 0.304 or 0.305. I'm a rounder. That's right, okay. So for arctan of negative 5 over 2, we want to switch colors. We're going to type in tan inverse in the same way. negative 5 over 2. You can convert that to a decimal. That would be negative 2.5. But we can also just use the calculator second tan. Negative 5 over 2. Enter. And we get negative 1.190. That's the only acceptable answer. Negative 1.190. That's it. And like I said, you can convert that to a decimal. Sorry, you can convert negative 5 over 2 to a decimal, but it doesn't matter. You can just type it in like that. Make sure you hit the negative key instead of the minus sign. All right, next. So here you go. Simplify without a calculator. Use the inverse idea would be the last hint. They are opposite operations. So sine of arcsine of root 3 over 2. What's arcsine of root 3 over 2? Arcsine of root 3 over 2 is, well, what makes root 3 over 2 out of sine? Pi over 3. But hey, now we're just going to do sine of pi over 3. We get root 3 over 2. So it's kind of like sine and arcsine cancel out. But you want to be careful about this. You want to be very, very careful about this. Okay, arctan 3, I don't know what makes 3 out of arctan. I really don't. But I know that tan and arctan cancel. Done. Now, when the inverse trig's on the outside, we have to be very, very careful. Careful when inverse on outside. So when the inverse is on the outside, we're going to be very careful. So for instance, our cosine of cosine, I'll go through it the old way again. Our cosine of cosine, we probably want to cancel them out and just get pi over 3. Let's see. Well, cosine of pi over 3, cosine of pi over 3 is what? It's 1/2. Arc cosine of 1/2, well, that's pi over 3. So maybe I was crazy. Maybe we don't have to be so careful. Well, check you real quick. Arcsine of sine of pi, 11 pi over 6. Arcsine of sine of 11 pi over 6. So if you went gung-ho and just said 11 pi over 6, you're exactly wrong. Nope. Ha 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 ha. It's not going to work out. So what you want to do is you want to be careful. Well, what's 11 pi over 6? What's sine of 11 pi over 6? Sine of 11 pi over 6 is negative 1/2. And this is going all the way back to the example that we want to go the angle that gets us negative 1/2, but is in quadrant 1 or 4. But wait, you say, quadrant 4 has 11 pi over 6. No. We're supposed to go with negative trig values. Negative angles. I'm sorry, not negative trig values. So negative pi over 6. So another way to do this is to say 11 pi over 6 was okay, but need right domain or range, right? We need to be in the right place, and 11 pi over 6 is not correct. We need that negative. All right, almost done. I think this video is going to be a little longer than the last one. It's okay. Arcsine of x squared minus 3 equals sine over pi over 2. Can you do this one yet? Do you have an idea of what to do? Go ahead and try it. Pause the video right now and try it. 3, 2, 1. The idea is use inverses. If that's enough of a hint, pause it now. Well, who is the inverse of arcsine? The inverse of arcsine is sine, and when sine's on the outside, everything's working out smoothly. When sine's on the outside, everything's going to work out smoothly, and everything cancels the way we want it to cancel in our minds. So I take the sine of both sides. I take the sine of both sides. I swear you better have taken the sine of both sides. That's the number one mistake I see. What's sine of pi over 2? Quick. 1. X squared equals 4. X equals plus or minus 2. Square root both sides. You have to remember the plus or minus. Have to. Super important in this course. Remember differential equations. They're coming back. Check that they both make sense. Arcsine of 4 minus 3. 4 minus 3 is 1. Arcsine of 1, pi over 2. Negative 2 squared, also 4. 4 minus 3, 1. Arcsine 1, pi over 2. Again, when we have sine on both sides, it usually works out nicely. Sine's the good one. It's kind of like if you start with a square root and you square both sides, everything works out. That's the idea. Here we go. This will be the last one before I cut the video. Promise. All right, sketch a right triangle and then evaluate without a calculator. I'm actually just going to do example 7. That'll make it a little shorter. So given that x equals arc cosine 2 over root 5, find tan x. Now, something I haven't had a chance to emphasize yet. Arc cosine, this is the ratio. That side is the ratio. This side is the angle. It's the inverse function. See, x is going in tan, so x is the angle for both of these guys. X is the angle, that's the ratio. So if I'm going to try to draw a triangle, it's a right triangle. X is the angle. And my ratio for arc cosine was 2 over root 5. Arc cosine, cosine, adjacent over hypotenuse. A lot of students I talk to haven't seen this ever before. Make sure you're following me here. Cosine's adjacent over hypotenuse. Arc cosine's giving us an angle and taking a ratio. So the adjacent side to x is 2. This is the opposite side. This is the adjacent side. This is the hypotenuse. It's across from the right angle. And now we're being asked to find tan of x. They want opposite over adjacent. So we need to find out the opposite side. How? What secret branch of mathematics teaches us a way to find this opposite side? This missing guy. Did you say Pythagorean theorem? Maybe I missed it. 2 squared plus our side, we'll call it y. Y squared equals root 5 squared. 4 plus y squared equals 5. Y squared equals 1. Oh, 4. Y squared equals 4. I meant to write that. No, I meant to write 1. What an idiot. All right, y squared equals 1. And so y equals plus or minus 1. Why can we rule out negative 1? Yes. Why? Because we know it's not going to be negative. Why do we know it's not going to be negative? Really think about it. Why can't this side, this y side, be negative? Not in domain. Negative 1, not in domain or the right quadrant. X. The right quadrants for cosine are 1 and 2, and y is never negative, right? The y value is not negative in quadrant 1 or 2. Like, this is what I'm saying. 1. We can't have our triangle going below the x-axis. because our cosine's only up here. Okay? That's what I'm saying. If you need more detail, please ask me about it. Please talk to me. I'd love to talk about it. So y is positive 1. And so tan x equals 1/2. It's wrong. It's wrong to sit here and find an angle. I don't know what angle this is. This is without a calculator. You have even less help on 8, which we'll do in the next video. Let's try to give you some problems. Great. You should be able to do up to try out problems. Oh, almost wrong screen. Try number 1 through 16. You should be able to try the problems 1 through 16. You should try them out, see if you have a feel for it, see if you have the basics down. Thanks for watching. Good luck on those problems. You have a nice night. You have a nice day. I'll talk to you later. Bye for now.